right, guys. Have a little mini lesson, video lesson, to get into the whole point of learning about radicals and multiplying them, dividing them, simplifying them, and that's to deal with special right triangles. Okay, so you're gonna need this sheet. This is a little lab we're gonna do to help us understand and derive and explore and make the connections with two types of special right triangles. And the first one we're going to talk about is derived from the basic shape of a square. So it says on this first part, it says, what do you notice about the triangle ABC? What basic shape is it a part of? So they're referring to this triangle down here, and I'm gonna go ahead and highlight that. So this triangle A to B to C. Sorry, that's a little crooked right there. It's part of what basic shape? Well, it's part of the whole square. And some things hopefully you recognize about a square is that it's a quadrilateral, meaning it has four sides. And if it's a square, then you're going to have all sides congruent and all angles congruent. In order for that to happen, that means you're going to have to be 90 degrees. And they kind of already indicated that with that right angle, with this box that they have here. Okay. So what they want us to do is label the A and the B and the leg, sorry, A and B, the hypotenuse C, and mark any congruency. So what we're going to do here, I'm going to change my font here. Your legs in a right triangle are the A and the B. And we did this, you probably recognize this with Pythagorean Theorem. And we're going to use that relationship to help us see the special rule with 45, 45, 90 triangle. That means if this is a square, all the sides are congruent. And we have all angles congruent, which means there would be 90, which they have the box there. So what we needed to add here was the tick marks to show which legs, which parts are congruent. And if I'm looking at just the triangle, they want us to classify this triangle by its side lengths. Well, the minute I see two sides congruent, then I know I have an isosceles triangle, okay? And the reason why we know that is we had two congruent sides. Forgive my handwriting here. All right, so now they want us to do some measuring here. Is it how big is the angle A to C to B? So they're referring to this angle. I'll do that right here, okay? I'm gonna have to undo that. Now remember, a square is 90, 90 all the way around, right? And if I now draw this diagonal CD, then hopefully you recognize that this has to be 45. And this would have to be 45. We're cutting those angles in half. So how big is ACB? That one is 45 degrees. How big is ABC? Again, 45. And then they want to know how big is C to A to B. Well, that's where we had that box. So that's 90 degrees. Okay. So we're going to calculate the lengths, express the number as a radical, okay, no decimals, using Pythagorean theorems, using what we know, that these two legs are always going to be the same. So we're going to start off with this first one. And I think we kind of looked at, maybe you did, maybe not, a relationship that occurs here. So if my AB, which is my leg, the B side is A, then this would also be, if that's 1, then this side it would also be 1. Okay, so to find the hypotenuse, okay, so just so we start off, this is the leg, this is the leg, BC is always going to be a hypotenuse. And what we've labeled it as is the C, okay? So our legs are the B and the A. All right, and our hypotenuse is always going to be C. So to work this out using Pythagorean theorem is when we did A squared, I'm going to write it over here, plus B squared equals C squared. This works for all right triangles, all types. Okay, so if I was to solve for the c, I'm going to do it in this table. 1 squared plus 1 squared is going to equal to my c squared. Okay, well, 1 squared is just 1. Okay, so really what I have is 1 plus 1 equals c squared, which we know is really 2, right? So I probably shouldn't have made some more room. Apologize about that. Oops, I didn't mean to do that. I was trying to go here. So let's just move this over a little bit. So I'm going to come over here. So what we have is 2 equals c squared. But to find just the c, okay, we are going to need to take the square root of that. And so that makes c equals the square root of 2. Because we want to keep our answer in the form of a radical. Okay, hold on. All right, so since because this is, for instance, not a decimal. So since we want to leave this in the form of a radical, this, in this example, this would be our final answer, square root of 2. Okay, so we're going to do that same relationship, but we're going to change the length of the leg, the value of the leg. So now we're going to do, what if the legs are 2? So if B is 2, then AC is also 2. So we're going to use Pythagorean Theorem, which would be 2 squared plus 2 squared equals c squared. Well, that's 4 and 4 equals c squared. So we're going to come over here to the side. So we're looking at the square root of, oh, sorry. I jumped again, sorry. We're looking at 8, right? 8 equals c squared, but to get to that c, let's take the square root of that. Okay. Now, in order to do that, this is where I'm going to have to simplify it. So I can simplify 8 with the factors of 4 and 2 when I take the square root of them. And the 4 is the perfect square. This is what we did before, simplifying. That perfect square comes out. So that means my answer here is 2 root 2 equals my c. And so we're going to keep that in the radical form, the simplified radical form. And what we want to do is try to see a pattern here, okay? You might have noticed it, but let's look at it with if I went to a side link of 3, okay? All right, guys, so I know some of you could probably do this part mentally. So, like, I know we're doing 3 squared plus 3 squared equals c squared. Well, 3 squared is 9, okay? So 9 plus 9 equals c squared, which means really I'm going to go ahead and write it in this small little, that's going to give me 18 equals c squared. And then I have to take the square root of that. Okay, and this is when we got to simplify that. So I'm going to come over here. Square root of 18 is 9 times 2. And that's my c squared that I took square of. But 9 is a perfect square. Take that out. So we get 3 root 2 equals c. Maybe you see it now. Hopefully you see a pattern here. Okay? Because if you do, we can jump. We don't have to do 4 or 5. So hopefully you see, if I know one leg, I know the other. So we obviously know that these two, the 2 legs are always going to be the same. But what the pattern we wanted you to see was that if I know the leg, okay, which is that number here, right? And every time when I'm working this out to get the hypotenuse, okay, it has a root 2 in its answer. And there's an association with that root. So hopefully, because if I had 2, then it was 2 root 2. If I had 3, then it was 3 root 2. And really, it's here too, because anything, I mean, there's a 1 in front of there. I don't really have to show that, because anything times 1 is 1. So hopefully we see that if the leg is 6, then instead of having to work it all out again, we would see that the hypotenuse here would have to be 6 root 2. Okay. I mean, I can do it. I would still do my 6 squared plus my 6 squared equals c squared. Well, that's 36. 36 and 36 will give me 72 equals c squared. Then I would have to simplify that. Okay. I could break that down. I'm going to move this 6c squared over. I could break that down into 36 times 2. Okay. Which I know 36 is a perfect square, which is why we have 6 root 2. So think about that. If my leg is 8, then the other leg is 8. Hypotenuse would be 8 root 2. If one is 10, then the other one's 10. Then this would be 10 root 2. So if I know any side link, okay, it doesn't matter. If I know, we're going to just say S is the side. Well, the other side link is going to be S as well. And to get the hypotenuse, it's always going to be whatever that side link is times the square root of 2. Okay? So I was hoping you could see that pattern when we're doing this. Now, so this is what we're going to get you to see real quick. To get the length of the hypotenuse, it is always the square root of 2 times longer than the leg. Now, if I know the length of the hypotenuse and I want to find the other leg, I'm going to now have to divide. Divide by, because I'm going to have to work backwards. So I have to do the inverse of time. So I'm going to divide by the square root of 2. So the rules I could write about the lengths of the sides of the diagonal of a square is that anytime we have 45, 45, 90, then it's always going to be the side link, the side link, the side link root 2. Okay. Now, we can kind of show that with the formula. Instead of using S, we'd use a different variable. And so we want to use this pattern to help us get to answers, maybe mentally, but just kind of see the relationship of when I'm going to multiply and when I'm going to divide on this table here. So we're going to look, should be look at the pattern with 45, 49. So sorry about that. I'll fix that. Okay, so a couple things. This X represents the leg, and I'm going to abbreviate hypotenuse with height, okay, hypotenuse. So that means what they're doing is whatever the leg is, they're putting it in front of the square root of 2. So right off the bat, if I know this leg is 5, then this is 5. Hopefully we know we just do 5 root 2, okay? So what I want to do, I want you to see if you can fill in the table, okay? I'm give you, let's just do the first 4 rows, okay? I'm going to pause, give you some time, and then come back and let you check. Okay, so hopefully we start off 10, 10, 10 root 2. And then this one, even though we have a leg that's a decimal, because the formula tells us that whatever in front of the leg is your X is that value, then that means this is the coefficient of the root 2, so that means each leg is 4.5. You can have a decimal, you can have a fraction to represent the leg. Now, some of you might have went ahead. Hopefully we see that same relationship even if the leg is a radical, but we got to remember to use our square root rule. So like if one is root 3, then the other leg is also root 3. But to get the hypotenuse, we're always taking that root 3 and putting it in front, which means we're multiplying it by that root 2. Okay, anytime there's numbers, you have a coefficient, a number in front of the radical, they're actually being multiplied together. Well, since both of these are radicals, then I can do inside times inside. So this becomes root 3 times root 2, which means the answer here is just root 6. So because we have radicals as a leg, we can multiply that to the hypotenuse because we're doing leg times square root of 2. Okay, so hopefully we see that, okay, these two legs are the same. If you want me to show the work, I can. But some of you probably did that mentally and just got to that root 10, which is great, because we're really just doing 5 times 2 underneath the radical. Okay, because they're both inside the radical. So same thing here. If this leg is 4 root 7, then the other leg is 4 root 7. So this is really going to be 4 root 7 times root 2. And the parts that get multiplied together are what's inside. Okay, so this becomes, you keep your coefficient, 4 root 14. All right. All right, now what if we have the hypotenuse and we got to get back to the leg? So anytime we're going from the hypotenuse to the leg, we're going to have to divide by the square root of 2. So I'm going to kind of do this over here on the side. To go, when we're going this way, we're multiplying. I think we saw that dots right here. So now I got to work backwards. I got to go back. So I'm going to work it out to the side over here. Since I know the leg is 2, the hypotenuse is 2, and I have to divide by the square root of 2. Now, we talked about this where it kind of ended on rationalizing the denominator. We can't keep a radical in the bottom, in the denominator. So what we have to do is rationalize that by multiplying by the square root of 2 over the square root of 2. All right, so when we simplify this, this comes out to be the 2 square root of 2 on the top all over 2. And then if I look right here, 2 over 2 can cancel out to just 1. So this would be root 2 and root 2. Okay, now there's a pattern with these two. It just depends on the number. So like same thing, if I have a 6, then I'm going to divide it by square root of 2. I can't keep it written that way. So that means I'm going to rationalize it. And maybe you'll see the pattern here. This on the top would be 6 root 2 over 2. And right there, that can be simplified. You can divide the 6 and the 2 because they're outside the radical. 6 divided by 2 is going to give you 3 root 2. Okay. Maybe you see it. Okay. But if not, you're just going to work it out and rationalize it. So once you try the last one, I'm just going to pause and let you give it a second. Hope you got 25 root 2. So the way I kind of see a shortcut pattern here is that if my 2, basically, if the number that is an even number, because I'm rationalizing, I'm going to eventually multiply the square root of 2, but I'm eventually going to get a 2 in the denominator. So if it can go into, basically it can, it's even, then I can really just, to get my leg, I'm taking half and then putting the square root of 2. So like half of 6 give me a 3, root 2. 25, half of 50, 25, root 2. So if it's even, you just take half. But if it's odd, then it's going to end up being rationalized, and you're going to have a radical answer, a fraction answer. So some things, some patterns I want you to recognize. It's just a relationship that happens depending on what part you're given and what part you're trying to find. So anytime you're going from a small to a big, in a right isosceles triangle, the big is always the hypotenuse. Okay, even in other types of special right triangle, the biggest part is always going to be it. The biggest part. There could be a bigger part, but the biggest part is always going to be the hypotenuse. So anytime that I am going from the smaller part, which would be my leg, to the hypotenuse, anytime I'm going small to big, you're going to have to multiply here. You're always multiplying. Oops, sorry. Anytime you go small to big, you're multiplying. It's going to be times. It just depends on the small part that you're given, okay? Anytime you're going from a big part to small, so you're getting smaller, right? So if I'm starting with the hypotenuse for this example, going to the smaller part, this is when you're going to divide. You do the opposite. So if you just remember, am I going to a bigger part where I'm starting from? Multiply. If I'm going to a smaller part from where I'm starting from, you divide. Okay. So now we're going to take these relationships that we saw here and this rule and understanding if I go small to big, I multiply. If I go big to small, I divide, to kind of apply it to actual 45, 45, 90 right triangles. So anytime I have this 45, 45, 90 triangle, this is what we call a right isosceles triangle. It's isosceles because these two legs are the same. Okay. To get the hypotenuse, it's always the square root times as long as the leg. So we're going to break this down in two parts. Our hypotenuse, I'm going to say h, is always equal to whatever our leg is times root 2. Okay. Now, to find our leg, so I'm going to do the opposite, do the inverse. To get the leg, our hypotenuse, I'm going to simplify this. We would normally divide by the square root of 2. So we're going to end up getting the hypotenuse times the square root of 2 all over 2 because we got to rationalize it. So if you're not good at rationalizing, but you remember this formula, you can plug in the parts as shown. And I'll show you on a couple examples here. So for example, here, they want us to find the missing parts. The part that I'm starting off with that's given is the leg. Okay, or the L if you want to call it that way. So that this means this would have to be 6. To get to that Y, it would have to be 6 root 2. Okay? I mean, once you know the rule, then there's not really a lot of work. It's only work when it doesn't fall into that root 2 format, when we have to kind of think backwards. So, for example, on number 3, I'm going from the hypotenuse, which we know is 7 root 2. I'm trying to get to the leg. So I'm going big to small. So if I go big to small, this is when I divide, right? So even if you don't realize just mentally, oh, anytime I see an x root 2, and that part is your hypotenuse, then the x that's in front would represent the leg. Even if you don't see that, you could still get there because I'm going from big to small. So my work here would be, oh, I'm just taking the 7 root 2 divided by the square root of 2. Well, those will cancel, and I get my leg 7. Okay, some of you probably saw it instantly, which is great. But if you're not, then you can kind of work backwards. So, like when you get here, let's look at number 5. Your leg is 4 root 3, which means this is also going to be 4 root 3. Okay, so to get to the hypotenuse, you have to take whatever that leg is, because the formula I gave you was whatever that leg is, multiply it by root 2. Well, in this instance, our leg is that 4 root 3. So I'm going to put 4 root 3 in place of the leg, and then I'm multiplying that by root 2, which is kind of what we did in the table when we had, what was our leg? I forgot. Was it 7? 4 root 7? Yeah, okay. So we're just going to multiply inside together. So this would be 4 root 6. And if it can be simplified, you simplify it. If it can't, then you just leave it as the radical. Okay? So what I want you to try to do is the remaining problems here using that rule. And then we're going to turn this in. So I do want all of this completed, and then we'll check it first thing in class tomorrow. I want to see what you kind of understood of this rule. All right, thanks guys.